In this example, we will solve a problem related to the concept of mass balance with reaction. We apply our knowledge on steady-state condition, identify the kind of reactor we are dealing with, and be able to correctly identify the boundary of the system or the proper control volume during the analysis. This problem is a continuation to the previous given example number 2 in the class, related to a sewage lagoon with biodegradation reaction. To recall, the previous problem was on finding the first-order biodegradation reaction rate coefficient K in a given sewage lagoon. We solved this problem by first drawing the schematic diagram of the system and inputting the details of the different parameters. As this is a continuous process at steady-state condition for a completely mixed flow reactor or CMFR, and for first-order reaction, the biodegradation rate coefficient was found to be 0.3456 per day, as you can see here. We solve this problem by either mass balance analysis or by the use of the CMFR equation at steady state. So let's proceed with the solution of this current problem. The current problem is about, based on the sewage lagoon problem, example number 2 in class, instead of one lagoon with 10 hectares, there are two lagoons in series with 5 hectares each and 1 meter depth. What biodegradation reaction coefficient must be achieved for a first-order reaction? Draw the mass balance diagram. For this current problem, instead of one lagoon, there are now two similarly sized lagoons at 5 hectares each, as you can see from the given in the problem, at 1 meter of depth. Arranged in series, which is Lagoon 1, shown in this schematic, and Lagoon 2. The question is to determine the biodegradation rate coefficient K for a first-order reaction for the two lagoons in order to maintain the same effluent concentration level of 20 milligrams per liter. So to solve this problem, we first visualize by drawing the schematic diagram of the system and add the numerical information and details. So if you remember the previous problem, we have the inlet concentration of 100 milligrams per liter, a volume flow rate of inflow of 8,640 cubic meters per day going into the Lagoon 1, and then a certain concentration goes out of Lagoon 1, which is now denoted as C1, and a certain flow rate of Q1 goes out of Lagoon 1 and then enters Lagoon 2. And then the final concentration is 20 milligrams per liter, and the volume flow rate is the same at 8,640 cubic meter per day. After we have made the schematic, we then list all the givens with their units, so as listed here, and as I mentioned already. And what we are supposed to find in this case, the biodegradation rate coefficient K, in terms of per day of a unit. To solve this problem, we need to identify what reactor we are dealing with and what are the conditions of the system. So as indicated in the problem, there are inputs and outputs in the system. We have input here, and then we have output here. So in this case, we can say that this is a continuous well-mixed flow and there are no losses or gains of water. Therefore, we can identify this system as a form of continual CMFR under steady-state condition. Knowing this information, we refer to the table here. As I've given in the class, this is a table for determining the different kinds of reactors at steady state, reactions at steady state. So for this, referring to the table, we then can get the equation for the final concentration Ct, which is C sub T is equal to C naught, which is this one, over the sum of 1 plus K theta. So this is now the formula for this system. From this equation, the theta, which is this one, is the hydraulic residence time, or the amount of time the sewage water with contaminant stays in each lagoon. So if you remember, we have two lagoons now at 5 hectares and 1 meter depth. Then, knowing from this different givens, we can convert this into square meters, the lagoons at 5 hectares. Then multiply by the depth to get the volume, which is in this case is equal to 50,000 cubic meters as the volume. Now we have the volume at 50,000 cubic meters, and we have a given of the volume flow rate at 8,640 cubic meter per day. then we can get the theta, or the hydraulic residence times, of 5.787 days. To continue, now that we know the hydraulic residence time, we can now proceed on the analysis of the whole system. As there are unknowns in the system, such as C1, in this case, C1 and Q1, we can divide the whole system into two control volumes. So how do we do this? We do this by the control volume for each lagoon to solve for the unknowns. But since it is steady state, Q1, since the whole system is steady state, Q1 should be equal to the inlet flow rate. So if you say here the Q inlet here, and we have Q1 and we have also Q out here, so basically all flow rate are the same for a steady state. So Q1 is equal to the inlet and outlet flow rate as well. So there are two ways to solve this problem for the whole mass balance equation, using a mass balance equation or by using equation for CMFR as given here. So we can also use a mass balance equation, and for a first order reaction as presented in the previous table. So for this instance, we will use the CMFR first order reaction equation as given here to solve this problem. So let's now proceed to the first control volume. For Lagoon 1 as control volume, the schematic diagram shows that C1 is actually the final concentration. Okay, as you see here, the final concentration, we can rearrange the CMFR equation for first order reaction into equation 1. So as we can see here, if the final concentration is actually C1, so this is the C1 now, this is the final concentration, so it becomes C1 for this. Similarly, we do mass balance for Lagoon 2. If we go for Lagoon 2, if you look at here, now C1 becomes the inlet concentration, okay, for Lagoon 2. And then Q1 is the same. So now we have C1 as inlet concentration. So we can rearrange again this formula, which is the same as this one, as becoming as the inlet concentration is actually C1 here. So before C1 is the outlet, now C1 is the inlet. So we have now two equations, equation 1 and equation 2. If you look at the two equations now, we have two unknowns, C1 and theta. So we have C1 and theta. But actually theta we have already solved already. So we have only one unknown left because we have theta of 5.787 days before that we have solved. So by manipulation of the equation, we come up with the equation to solve K. Okay, we can manipulate these two equations. So by combining equation 2 to equation 1, we can then have this equation as a final equation of K theta is equal to the square root of C naught over CT minus 1, basically. So from here, what we have left, because we have eliminated C1, because C1 is actually equal to this part if we combine equation 2 and equation 1. So we have eliminated C1. Now everything, all parameters are in terms of C naught and C sub t, K, and theta. So we have theta, we have C naught, we have C sub t, and only K is left, right? So from there, we can now actually input all the different values into the formula, which is equation 3 now. So we have C naught at 100 milligrams per liter. We have final of 20 milligrams per liter and square root of that. And then minus 1 over the theta, which is 5.87 days. 787 days, I'm sorry. So everything, if you calculate this one, the K is now 0.2136 per day. So now we have, once we can also use a mass balance approach to actually solve this problem instead of using this formula here. All right? So this example shows how we design a system to maintain the desired quality of effluent water. So coming from one lagoon only, we can now determine the K, or the biodegradation rate constant, for two lagoons. We have applied steady state conditions and first order reaction rates for a completely mixed flow reactor in this problem. This exercise also showed the importance of correct control volume identification to help in the overall analysis of the problem.